Welcome back. This time we're going to round off our study of three-dimensional solids by taking a quick look at some spheres and hemispheres. So let's bring a sphere in, and the first thing we're going to notice about this solid is that it is not an example of a polyhedron. It's got no faces, no vertices, and no edges for us to work with. Now, at first glance, that makes this object really a very simple three-dimensional solid. But that simplicity is going to have some issues when it comes to the formulas that we're going to work with, specifically in deriving them and building them. Like, to build the formulas that you're going to see today really requires some calculus, some pretty advanced calculus for some of them, and so we're not going to be getting into that today. That's beyond the scope of this class. Instead, we're going to be focusing on what the formula are that you need to know about this object and when to use them. If you would like to know more about where the formulas come from and how they're built, then I'm going to include some additional video resources in the description below. If you want to study on your own a bit, sort of extend, those videos will be a very good starting place for you. Now, the first formula that you're going to need to know for the sphere is for the volume. Now, the volume of any sphere can be calculated by taking 4/3 times pi r cubed. That's your first formula that you need to know. Your second formula is for surface area. Now, the surface area for any sphere is always calculated as 4 times pi r squared. Now, these two formulas have got some differences between them. In addition to the power that you're raising the r to and the coefficients that they work with, but there's one really big thing that these two formulas both have in common, and that's the fact that both formulas have only the one single variable. So if you know the radius of your sphere, you can instantly calculate both the volume and the surface area of that sphere. So working with these formulas is pretty straightforward, a lot more straightforward than a lot of the other solids that we've been working with. You just need to know one thing. So if you're not given the radius of a sphere, your task is going to be finding the radius, and if you are given the radius, then you instantly know both volume and surface area. Okay, so now let's take a look at the hemisphere. So bring a hemisphere in. Now, a hemisphere is defined as being half of a sphere. So you can create two hemispheres from any single sphere by splitting it along one of its circumference lines. You get two congruent hemispheres from any one sphere. So since a hemisphere is half of a sphere, that's going to change both the volume and the surface area formulas from the full sphere. So let's start with volume and make the adjustments that we need to create a new formula for the volume of a hemisphere. Now, bear in mind that a hemisphere is, by definition, half of a sphere, so its volume would be half the volume of the original sphere. So the formula is going to need to be adjusted, and instead of 4/3 pi r cubed, the hemisphere is going to have a volume of 2/3 pi r cubed. Because it's exactly half of the 4/3, so this time it's 2/3. Moving on to surface area, again, bearing in mind that a hemisphere is defined as being created from a sphere that's been split in half, the surface area is going to be 3 pi r squared. That's right, 3, not 2. Now, if you were thinking, well, the hemisphere is half of the sphere, so it should have been 2, right? I mean, the original sphere definitely was 4 pi r squared. Why don't you just cut it in half? Well, there's a pretty good reason for it. I'm kind of beating around the bush here because I want to give you enough time to think about it yourself, but I will go through the brief explanation for why the surface area is not simply half of the original sphere. Now, the problem is in how the hemisphere is created, or at least the difference is. It's not really a problem. But what happens is that the original surface area for the sphere, that described this entire outer shell. So all of this outer shell was included in the surface area of the original sphere. When we cut the sphere in half to create the hemisphere, we do get that half shell, which is going to be 2 pi r squared. But the hemisphere is not just that half shell, because we also have this cross section down here, this base, this new face that's been created, this circular face. And we have to include that in the surface area because that is an exposed surface. Now, in a sphere, or in a hemisphere rather, this face is always just going to be a circle. It's just going to be a circle with the same radius as the original sphere, so its area is pi r squared, because it's a circle. So when we go to calculate the surface area, just like all of the other solids we've worked with, we take the sum of these two regions. We've got the 2 pi r squared from that outer shell, but we also have the 1 pi r squared from the new face at the bottom. Now these two terms are like 2 pi r squared plus 1 pi r squared. That's where we get that surface area of a hemisphere is 3 pi r squared, not just 2. So there you go. Those are all of the different formulas that you're going to need to know how to work with when you're dealing with spheres and hemispheres. I'm not going to go through any worked out examples here because these objects are pretty straightforward. All 4 of these formulas, depending on how you count, are just in terms of the radius. So as long as you know the radius of the object, then you can work with it. So that's all I have for you today. Thank you very much. Good luck and have fun.